Hello, my name's Samuel Beck, and today I'm going to be going through the steps to solve a simple principal-agent problem, as well as highlighting some of the insights that we can garner along the way. So before we get into the problem, it's important to understand the variables that we'll be working with. So the first variable that we should get a good understanding of is the expected value of output for the firm, which is equal to the expected value of effort exerted by an agent, A, times by how much impact that effort has on output, K, plus some exogenous shock. So because the expected value of Ka is equal to Ka, we can deduce this. The expected value of output is equal to Ka plus the expected value of the shock. And as the expected value of the shock is assumed to be 0, because it's normally distributed about a mean of 0, we have the expected value of output equal to Ka. The next variable that we should get a good understanding of is the expected value of wage. So that's the wage to the agent, and that's found by the expected value of the fixed component of salary plus the level of incentives times the level of output. So here we're assuming obviously that output is observable and contractible. So the expected value of salaries plus the expected value of the incentives times the expected value of output is going to be equal to the expected wages. Likewise, in the last problem, the expected value of salary and incentives are going to be equal to their true value, which leaves us with the expected value of wages equals salary plus incentive level plus the expected value of output, which, as we found just recently, is equal to the expected value of, so the expected value of wages are equal to S plus BKA. So the simplest variable that now we're going to understand is the variance of wages, and that can just be found using simple expected variance laws, which is equal to beta squared times the variance of the shock. So now that we have this information, we can go about setting up the problem for the principal, and that's going to be equal to, they want to maximize the level of incentives that will give them the biggest possible expected output minus the wages they have to pay the principal for that output. So that isn't unconstrained, however, and it's subjected to this individual rationality constraint, which says that, look, the agent's only going to exert effort so long as their expected wages minus their level of risk aversion minus the cost of that effort is greater than or equal to their outside option, which in this case is 0. And the other constraint is the incentive compatibility constraint, which says that the agent is going to choose the level of effort which maximizes their utility, and that is just going to be equal to the argument of the maximum for A for the certainty equivalent. So we can play around with that because of the information that we started with. That is the better understanding of the variables. So we can find that we really want to max B equal to the expected value of output minus the expected value of wages. Also, we can use the expected value of wages, output, and the variance of wages to rewrite our individual rationality constraint in terms of S. You'll notice that it's now an equality, not an inequality. And the reason of that is that we assume that the individual rationality constraint binds because the principal will pay the agent perfectly to make them indifferent as to their outside option. So the incentive compatibility constraint looks vastly different, and the reason for that is that we've gone about the argmax. We'll set the first order conditions equal to 0 and then rearranged in terms of A, and that's how we get this level of output that we say is optimum for the firm, given the agent certainty equivalent. So from this information, we can substitute both of the constraints into the maximization problem, which gives us this. Now the agent wants to maximize the level of incentives to maximize this equation, which is just those two constraints substituted in. the first order conditions of which can be found as, this, k squared over 2c minus br variance of epsilon minus bk squared divided by 2c. And we can set that equal to 0 and rearrange for b to give us the optimum level of incentives are equal to k squared divided by k squared plus 2cr variance of the shock. So this makes intuitive sense. It says that if we find that the risk for the agent increases, the level of risk aversion increases, or the riskiness of the market, well then the optimum level of incentives are going to decrease because they won't have as much impact on motivating the worker. Also, we find that if C increases, so that is effort becomes costlier, well then incentives will also have less impact on motivating the worker. So now that we have this optimum level of B given our information, we can go about substituting that into the optimum level of, the optimum level of effort that we found earlier. So now A star equals that B star we just found times K over 2C, which we can really expand out as to A star equals K over 2C times B star. So with these two, we can substitute them back into our individual rationality constraint from quite a while ago, and that gives us the optimum level of the fixed component to the salary. So that is going to be equal to pretty much the individual rationality constraint we had initially, except now we're using those optimum values of B and A. So now that we know these numbers, it's important to compare it to our first best scenario. So the scenario in which the principal and the agent maximize the total output. So we find that the efficient level of output, that is socially efficient, is given by the maximum of the maximum utility of the principal plus the maximum utility of the agent. So we can add these together and then solve for A. So this is the first order condition set to 0 and then rearranged. And we find that the socially efficient level of effort is equal to K on 2C. So what do we notice? Well, we notice that that's different than the socially optimum level given for the firm, which is K on 2C times by B, which is this. So this actually makes intuitive sense. Because the agent is risk averse, well then the optimums aren't going to be reached due to this introduced risk aversion. The agent won't put in the optimum amount of effort because effort has a certain cost which is incurred for sure, whereas the utility gained from the output is prone to shocks. So if there was no shocks, so if the variance of epsilon equals 0, well then the agent will put in optimum effort. So the agent would also put in effort if they weren't risk averse. So with a risk environment and a non-risk neutral agent, the optimum level of effort will therefore not be applied. And it doesn't matter which values we give to K, C, or R, so long as R is not equal to 0 and the variance of the shock is positive, we will not ever reach the optimum level of effort exerted. So I think this is actually one of the profound implications of this model, and hopefully it has somewhat resonated as well. So thank you very much. Have a great day.